Today we'll talk about the semiconductor physics and what is semiconductor physics. So we'll cover a lot of different subjects and I divide it into three. First, we'll identify the charge carriers in solids and formulate the role in the current flow. I'll explain what doping is, and also we'll explain what the transport of carriers, basically electrons and holes in a semiconductor. We'll also talk about the p-n junction and how a p-n junction works in reverse and forward bias conditions. And we'll also illustrate an IV characteristics of a p-n junction. So semiconductor devices basically serve at the heart of microelectronics, and p-n junction is probably the most fundamental semiconductor device. So we'll first talk about the crystal structures, band gap energy, and holes and electrons. And then the intrinsic semiconductors, mostly we'll talk about silicon. And then we'll talk about other extrinsic semiconductors, such as phosphorus, and how we mix it with silicon and make doping possible. And then we'll talk about different transport of carriers, such as diffusion and drift mechanisms. So to understand the IV characteristics, basically current voltage characteristic of a p-n junction, we need to understand its physics, how the electrons and holes behave inside the p-n junction, and what happens when we increase density of the holes or electrons inside the p-n junction to change the actual transistors, because like basically the transistors or the diodes or anything you see in the PSpice is actually it's a model, right? It corresponds to actual physical device, and this device parameters heavily depend on the semiconductor physics. And looking at the periodic table, as you remember from chemistry, there are different atoms. There are like 3, 4, and 5. And if you look at the silicon, silicon is just like carbon. It's in the middle. And the bonds, like the aluminum, gallium, boron, they have 3 electrons in their outer shells. And both and phosphorus and arsenic, they have 5 electrons, 5 valence electrons in the outer shell. And looking at the next picture, as we mentioned, silicon has 4 valence electrons. That means silicon can bond with 4 other different silicon in covalent bonds. And when the temperature goes up, these electrons in the covalent bonds can become free, which means they get excited by hot temperatures and the bonds get broken, and these electrons start to become free agents, right? So these electrons become free agent means they cause currents at some point, because flow of electrons cause flow of currents. For instance, when we look at this different electrons, we need to know what is the electron-hole pair interaction. So when there is an electron released, let's say at t equals t1, when that electron gets out of that bond, that leaves a hole at that point, at that bond. And that another electron, let's say here at t equals t2, fills that hole, right? So when that fills that hole, let's see, let me draw it. When that electron fills this hole, then now there is another hole here, and then another electron fills that hole, and then there is another hole here. So this actually causes the flow of currents. So as you can see, when the electrons move, also at some points, holes also move, right? So you can see here, electron is moving from right to the left, from right side to the left side. Actually, it moved from here to here, but the hole actually moved from here to here, right? And that is basically the definition of the current. And always holes flow opposite to the electron flow. And let's see. The next slide shows that these number of electrons and holes available in a structure is actually defined for certain temperatures, and it changes according to the semiconductor. So if we look at the silicon, it's defined by this formula, and I equals a number times the temperature comes into effect here, and also there's an exponential of minus band gap energy divided by 2K temperature. So what is band gap energy? Band gap energy determines how much effort is needed to break off an electron from its covalent bonds. So if the structure like a silicon or carbon or any other one, they have different band gap energies. And let's say silicon, or like let's say it's an insulator, okay? It's a very it's an atom that doesn't want to bond. It's basically helium, for instance. So it has a very high band gap energy because it doesn't want to interact with any other atoms, right? So when this Eg is very high, that makes this term very small, and that means this term gets very small. So the higher the band gap energy is, the smaller free electrons exiting in that structure at a given temperature. So as you can see, for different temperature, we have different free electron densities. At 300 K, we have 10 to the power 10. At 600 K, we have 10 to the power 15. So why? Because when we increase temperature, we excite the electrons and they tend to break their bonds, right? So then we basically excite that structure with currents. So the next slide is showing what doping is. So the structure doesn't always have to be silicon and silicon, right? Silicon can form bonds with other structures. So in this case, it's phosphorus, and phosphorus have more valence electrons than silicon. Silicon was 4A in the periodic table, but phosphorus is 5A. So 5A means when they bond, it still has one extra electron. It's in the valence, so it becomes available in this structure. And you don't really need a lot of energy to move this electron because now it's already available. It's not even in a bond, right? So you can easily excite the structure and create current. Then we can dope this structure. Basically, doping is adding another structure other than silicon. So if we dope it with boron, boron is a 3A, so it has one less electron than silicon. So when it bonds with silicon, actually, it bonds with using its 3 electrons, right? But then it cannot bond anymore because there are no more available electrons, but silicon has 1 electron. So that means boron has 1 hole actually, because when it doesn't have an electron, the silicon becomes like silicon tries to bond with boron, so it creates a hole. So to summarize these charge carriers, we can dope silicon with different crystals, with different materials. And if we dope it with, let's say in the periodic table, 5, 6, 7 structures, we'll have more electrons flowing. But if we dope it with 1, 2, 3 in the periodic table, 1A, 2A, 3A, then we'll have more holes in the structure. And the structures like phosphorus, they're called donors because they are more n-type. It has more electrons in its structure. The other ones, like the one with the 1A, 2A, 3A, they are called acceptor because they have less electrons in their valence shells. And The one in the left, you can see electrons become the free majority carriers, and in the one right, the holes become the free majority carriers. So we have this formula, and it says that the number of electrons times number of holes equals always the number of free electrons times the number of free electrons square. This is a formula valid for every time, but at different temperatures. So let's say the majority carriers are borons, right? So we add Na, like, so that this is the number of added borons. That means it has this many holes in the circuits. So we can kind of equate to each other. If we have majority carriers as phosphorus, and then we have that many electrons available in the structures because we're doping with them. So adding those atoms, so each of them creates one electron, right? If we add another structure with 2 electrons available in their outer shell, then this would be 2n, right? Because it is 2 electrons and times each atom. And when we dope it, let's say with phosphorus, then when we look at the minority carriers, we use this formula. So if we try to find P, well, it's obvious, Ni times Ni square divided by N, right? So, and N equals Nd, so we can write it like that. And similarly, if it is P-doped structure, the minority carriers will be electrons. So the free electron square divided by the acceptors will be the minority carriers, which is electrons in that structure. So do you have any questions so far?
Can I ask a question?
Yeah, of course.
Carbon also have 4 free electron. Why we use silicon instead of carbon?
Well, we can use carbon too. There are just different structures. Actually, carbon has, you're right, it has also 4 electrons, but it is band gap energy is also different. So for some reason, I think the silicon is also cheaper, like and it's found in certain elements more, like basically its existence is much more. I believe that's why we use silicon. I think honestly, I'm not 100% sure about the answers. I know structures that use carbon, but I think the biggest reason is the price. So the silicon is a much cheaper. Copper is silicon, for instance. So that's why we use mostly silicon for these structures.
Thank you.
No problem. For instance, germanium is also used a lot in the military, but military doesn't care about the price. So mostly germanium structure provides much better circuits and systems because their performance is much higher. That's why in military they use germanium, but in mobile electronics, like consumer design, like cell phones, TVs, game boxes, they usually design all these circuits with silicon because it's much cheaper. So what is drift? Drift is our first charge transportation mechanism. What is charge transportation mechanism means? It means how the electrons or how the holes move inside the circuits. So as you see, when there is a voltage connected to, let's say this is a copper, we excite this system, we excite the structure with electric fields. And when there's an electric field, these structures, like let's say these are electrons going this way, and then holes going this way. So holes going that way and electrons going this way, this creates a current. But the speed of the holes and electrons are different. Okay, because electrons are much more mobile than holes, right? As we checked in the previous slides, the electrons are actually like they are available already when it's bonded, but holes mostly exist inside the bonds. So holes don't really move, like they are moving triggered by electrons. So an electron has to fill a hole so that hole moves, right? So electrons, that's why there's the mobility constant is much higher, which is this UN, like mu n, sorry, compared to mu p. So, and when we calculate their speeds for a same electric field, you'll see that because of this, electron speed is much higher and they move much faster than holes. That's why you'll see in the previous chapter, we have a transistor called NMOS, which is basically working with the principle of electrons moving. And then we have a transistor called PMOS. And that's basically based on the hole moments. And the PMOS devices are much, much slower than NMOS devices because they base on the hole moments. As you see, their velocity, though, they are both proportional to the electric fields in the environment. So looking at it in a cross-section way, we said, for instance, this is a copper, right? And when we take a cross-section and we look at different time slots at t equals t1, and then at t equals t1 plus 1, we can say that a chunk of currents flowing, a chunk of piece at where the current is flowing, it moves, let's say, from x1, and then 1 second later, it moves like, where is it? It moves, okay, a certain amount in the x direction. So when we calculate the current, we have to look at the cross section because the charge is defined in terms of density. So the definition of charge is Q, right? And the definition of the charge is in density. So we have to find the cross section, which is W times H. So W is this width and H is the height. So this shows that the cross section here, right? And that cross section is that area per unit X. So when we multiply that charge with that cross section, basically we find the total charge in that cross section. And when we multiply with the number of free electrons, right? Then because every electron has a charge Q, the n number of electrons has a charge nq. If we look at how much charge exists in that cross section, we have to multiply it WH. Then the velocity comes here. These charges move. So let's say if it moves 1 centimeter per second. So that is the x dimension. So in 1 second, it moves 1 centimeter. So we basically make it from 2D to 3D, right? We bring the x dimension into the equation. So, and the current is always defined per second, right? It's the derivative of charge. So it is the charge flowing divided by time, or the charge derivative with respect to time. So this, we don't write the x dimension here, but instead we write the speed, because that is the derivative of x dimension with respect to time. So we can write here v, which means the x dimension that the charges took divided by how much time they took. So in 1 second, that is called velocity. So basically, in other another way to explain this, we multiply x, width, and height, like we basically multiply 3 dimensions, length, width, and height, but we divide it per time. And that is the term in the square. Then we multiply it with the total charge in that system flowing, which is number of electrons times Q is how much an electron has charge in terms of coulombs. So that's how we calculate the electric currents in terms of charge. Do you have any questions? Okay. And this is called drift. So how these holes and electrons move with respect to electric fields. And when we look at the previous equation, we calculated in terms of current, but there is this term also called current density. So current density means we divide that current again back to the cross section. So, and here, as you can see, we have N times Q, and that is the total charge. And we have the mobility of the electrons, and we have the electric field. And this is for electrons. We also have the same thing for holes, right? So the total current is the combination of both electron speed and the hole speed. So when we write this for electrons, and when we write this for holes, right? So this is for holes. So this is for electrons. So when we sum them up, we can find the total current density. And that is basically this. So the total current density consists both electrons and holes, okay? It's not just electrons or it's not just holes, because both of them will be moving. Okay. So the mobility for both electrons and holes actually saturates at some point. It's not a linear equation. So when we apply electric fields, that electric field excites the electron, and a stable electron that's not moving starts to move, right? And for instance, let's just draw like 2 plates, and let's say this is plus here, and let's say this is minus here. Okay, so now this creates electric fields, right, from plus to the minus. And when it does that, it's like this. We call it electric fields. And then when we put the electron here, E minus, what happens is this electric field starts to move this electron in this direction, right? Because plus attracts minus. So, and this electron now starts to get faster and faster. So, but it comes to saturation eventually. It cannot get faster in infinite amounts. And this thing we call is Vsat. So every electrons and holes come to a speed of saturation. They saturate, and we define this in terms of equations. And the equations are defined as terms in terms of mobility. So we call this thing mobility constants, mu0, and we divide it by 1 plus BE. B is just a constant, and E is the electric field. And we have this term called Vsat, which is a saturation speed. So it's good to write mobility rather than mu0. It's good to write it like that, so we know that it's a function of electric fields. Okay. We'll get into this more in the next lectures, but I think it's good to know this much at this point, that electrons and holes come to a saturation in speeds. Okay, so velocity doesn't increase linearly with electric fields. It will eventually saturate to a critical value. Okay, so the next slide shows the second transportation mechanism, and it's called diffusion. This is like just flow of water, right? When there is more water at some point, it will flow from more to the less. So same principle. When there are more electrons or holes at some points, they will start to flow from more to the less. And this is called also diffusion in the semiconductor material. So when we inject carrier from one point, that carriers will start to flow towards less, and it will start to form a non-uniform concentration in a junction. So if we inject the carrier from middle, then it will flow both sides, or actually you can think it in 3D. If it's not just one single wire, let's think it as a square, then it will flow every direction to fill the places that don't have electrons or holes. So in summary, charged particles move from a region of high concentration to a region of low concentration. And as I mentioned, it's very analogous to a water flow. So the next slide is formulating how diffusion can be modeled. So the electrons with respect to X or Y, we can think in 3D, does matter in this point because we are trying to write the current flow in terms of diffusion, right? So the diffusion current is proportional to the gradient of charge, which is dN over dx along the direction of the current flow. And the total current density consists, as I mentioned before, both electrons and holes. So this is the current due to the diffusion of electrons, and this is the current due to the diffusion of holes. And when we sum them up, actually, I'm sorry, this is the current due to the flow of electrons, and this is the current density due to the flow of electrons. And if we look at the current density, J, due to the flow of holes, that would be this term. And when we calculate the total current density, just like we did with the drift, we gotta sum them up, and we come to an equation for the total current density. Okay, any questions? Okay. So you can probably wonder what is D, what is these terms and stuff. There are certain constants which you'll learn in the Einstein relation, which is coming soon. And when we look at the linear and nonlinear charge density profiles, it doesn't have to be linear like that, right? Depending on the injection type, it can either take a linear curve or it can take a exponential curve. And this linear charge density profile means if it is linear, it's basically constant diffusion currents. And if it is nonlinear, it's basically varying diffusion currents. And it is given to you per semiconductor. So every semiconductor will have different characteristics for diffusions. So to summarize it, we have two transport mechanisms. One of them is drift currents, and the other is diffusion currents. So this one and this one creates the velocity for electrons and holes. And these electrons and holes form a current. And as I mentioned, the mobility of the electrons and mobility of the holes are described with these mobility constants. And also the diffusions are also defined with these constants. And we have this thing called Einstein equation. And Einstein equation tells us, it's a long formula, and I can probably send you the proof for that. But Einstein formula says that drift currents, like the mobility constants, are somehow related to the diffusion constants. And this KT over Q we'll see it a lot in the future. It's a term called VT. It's called thermal voltage. And right now it's just enough to know this much. These mobility constants and diffusion constants are somehow correlated to each other. And this thing is called Einstein's relation. And when you are asked to calculate, for instance, the temperature, these diffusion constants and drift mobility constants are also they are functions of temperature. So when we look at mu, this is also a constant of temperature, right? So it's equal to mu zero times function of temperature. So just make sure that don't write just the constants here, but also write what it is at that temperature. Okay. All right. So the next slide is getting into the p-n junctions. Do you have any questions so far? Okay. No questions, seriously?
Hocam chatte bir soru var.
Chat'te bir soru var. Okay. Majority minority tunnel konseptini tam anlayamadım. Okay, let's go back there. 1 second. Okay, so you remember from chem how covalent bonds, bond forms. So this is a structure, a silicon structure, silicon crystal, and they form with each other. And if this silicon bonds with something else, for instance, with phosphorus, there is an electron available outside. And the reason is phosphorus has 5 electrons outside. And it uses its 4 electrons to bond with the 4 electrons of silicon. So what happens to the 1 electron outside? It becomes available. So that means every phosphorus atom we introduce to the structure, we create an electron. So the number of donors, this is called donor for if it is phosphorus, equals the number of electrons. So if we look at the similar thing with boron, boron has 3 electrons, but silicon has 4 electrons. So boron forms bonds with 3 silicons and gives its 3 electrons. And silicon bonds completely okay here, as you see. But this bond cannot form because boron doesn't have an electron to give silicon. So, but the silicon has 1 electron available here, right? So, but the electron is not moving. That silicon electron is not available because the structure of the silicon is not, the electron is not excited. So we call this structure as p-type because boron is missing 1 electron and basically it fills the silicon's electron with the hole. So there is a hole here basically pairing with the silicon's electron. And this hole is equal to the number of borons because boron is only missing 1 electron to form with the silicon. So how many acceptors we introduce becomes how many holes becomes available in that structure. Okay, so as you can see, summarizing, if we provide phosphorus, like n number of phosphorus, we introduce n number of electrons in the circuit. If we introduce n number of acceptors, for instance, borons, we introduce n number of holes as a majority carrier. So majority carrier means, just like the name says, the holes or electrons are more in that structure. If it is electrons are more, then electrons are basically majority carriers, holes are minority carriers. If the opposite, if the holes are much more than electrons, then the majority carrier is basically holes. Okay. So again, what matters is, as I said here, let's say we added n number of borons, that becomes that many holes in the structure, and Ni square doesn't change. It is a function. It changes with temperature, but it is specific with certain structure. For instance, silicon has a specific Ni. Let's say carbon has a specific Ni, and so on. If we increase the temperature, this Ni will increase. And so let's say I give you the number of Ni. I tell you it's silicon and it has this much Ni at this much temperature, and I tell you I dope the structure, I dope the silicon structure with n number of phosphorus, and that number of phosphorus becomes the number of electrons, because we doping it with a lot of atoms that will provide the same number of electrons. So basically we now know what is n, but we need to find the p, because p is now minority carriers. So we find p from this formula, or vice versa. If we dope it with boron, then the p's, the holes, become majority carriers, and the minority carriers become electrons, and we find it from this formula. Okay. Okay, so let's see. Oh, we did go so much. Okay, we were here. We talked about Einstein's relation here. So Einstein relation is again saying that the drift and the diffusion constants are related to each other. Okay, and basically, when we want to calculate the current, the total current in a structure, we both need to consider the drift current mechanism, and we need to consider the diffusion current mechanism. They both, are factors of the currents. They both are mechanisms that contribute to the currents. And I think that's it for the Einstein relation. Now we can get into the p-n junction. Before we get into the p-n junction, I think we can give a 5-minute break. Then we can do the quiz after 5 minutes. Then we can continue with the p-n junction. Okay, we talked about the p-n junctions when we first start the chapter. So p-n junction is at the heart of the electronics, as we mentioned. And what's p-n junction? P-n junction is a semiconductor, and it is doped in different way. So there is a p part and there is an n part of the junction, and p part is doped with borons or any kind of acceptors, and n type is doped with phosphorus or similar donors. So when we dope it like that, basically we provide holes and electrons at either side of the junction. And how we represent this p-n junction is with the symbol. The plus side, or the p side of it, is anode, and the other side, the n side or minus side, is cathode. And you'll see in the PSpice this symbol, or you'll see in the homeworks a lot. And when you look at this figure here, you'll have so many holes doped into the p side, and you will have a lot of electrons in the n side. And the p-n junction is invented in 1940, and actually the guy, Russell All, he melted the silicon to achieve a high purity. And when he was cooling it, he realized that p-type and n-type impurities redistribute themselves, creating a p-n junction. So basically, somehow during the cooling process, he was able to get this p-n junction. And then he observed that when this junction got exposed to light, which is an energy, right? The current start to flow. And basically he realized that something is going on, and this lead to invention of digital camera, because digital camera works the same way, right? Digital CMOS, like the junctions see some light and it turns the electrons, so the intensity turns to current, and then you were able to get a output out of that. So the diodes or the p-n junction operates in 3 different regions. There is a p-n junction in equilibrium. There is a p-n junction under reverse bias, or the p-n junction under forward bias. So we will go through all of them one by one, what they mean. We'll first talk about equilibrium, and we'll talk what is a depletion region and built-in potential. Then we'll talk about reverse bias, and we'll talk about the most important functionality of the reverse bias, which is the junction capacitance. And then we'll talk about the forward bias properties, and we'll talk about how the p-n junction or the diode characterized in terms of current and voltage, which is called IV characteristics. So in order to understand the diode, you need to understand all the 3 operation regions, and probably when you start doing your lab, you will have a chance to play with the diodes and see how it functions as well. So let's go to the next slide. When we form the p-n junction, you'll see that when it is doped with acceptors at the right side, the majority carriers of phosphorus, then that means it is electrons. So that means pluses are here, and that means minuses are here, right? And when you look at the characteristics of the p-n junction, you'll see that there are minority carriers, which we studied in the previous slides. So what does minority carriers mean? When there are majority carriers holes at the right side, as you also did in your quiz, there will be much less minority carriers present, and vice versa. When there are electrons in the n sides, there will be much less holes. And we already learned how to find the numbers of these. Their multiplication equals to the free electrons square at that specific temperature. So these characteristics, when you look at it, causes a concentration gradient, right? Because there are majority carriers at one side and there is less, and vice versa. Holes are more here compared to others. So we learned what is the diffusion current is, right? Diffusion means flowing of more electrons or holes towards the other side where it is less, towards the minority. So basically in equilibrium, there is this diffusion current, but actually not. If you don't apply a voltage, you don't see a current. So there should be a reason why there is no current when a diode is not excited. So looking at it, as we leave this p-n junction in its neutral form, this is how it is at t equals 0. When we wait a bit, and when t equals t1, we start to realize that actually the electrons and holes are somehow combining with each other, and then we have a depletion region. Depletion region means there are not holes or electrons, but only ions. So electrons start to leave this way, like basically holes start to leave other way. So the electrons at this region, they go away, and holes in this region, they go away. And there is this junction called depletion region, and it is left side is with positive donor ions, which is phosphorus, and the right side is negative acceptor ions. And this field, this region, creates an electric field because left side is pluses, right side is minuses, right? So this electric field is now existed in this depletion region. And when we wait quite a bit of time, we call it T equals infinity, this depletion region comes to a saturation. It doesn't form anymore. And now we have this part free of holes and electrons. So looking at the next slide, we will realize that this depletion region actually prevents the diffusion current at some point, because in this region, actually, in the actual PN diode, these holes are more, right? They will want to flow here. And these electrons are more, and they will want to flow here, right? But they cannot, because these junction, as you can see, the pluses will push them away, the holes. Plus pushes pluses, right? So pluses won't be able to flow, and vice versa. If you look at the electrons, they will want to go here, but there is a junction here with full of electrons, and this junction will push them back. Basically, it will force them not come at all, right? So that's why in a neutral, not excited PN junction, we don't see a diffusion current flowing, because the depletion region forces those electrons or holes go back. So if you look at the electromagnetics or 202, I don't know if the instructors studied that, but I attached the appendix where you can watch 2-3 minutes of videos and remember how the electromagnetics, electric field, voltage, and so on are related. So voltage is an integration of electric fields with respect to x-axis or with respect to space. So when you look at this depletion curve, you'll see that there is an electric field, right, between minus B and A. And the electric field is actually maximum in the middle, or it's maximum at some point in the middle. And the reason is because if we look at here, let's say this part, there are a lot of ions with positive, and there are actually none with negative ions, negative charge ions. So we don't really get to see the attraction between those ions. But when you look at right in the middle, all of them are, like, let's say we put a charge here. Let's say we put a minus charge here. So then all these plus signs will be attracting this minus sign to the left, and all these minus signs, minus ions, they will also push this minus sign to the left. So you'll see all of them will contribute towards the electric field. So that's why if you look at this figure at the bottom, you can see that at some point in the middle, which we call it zero junction, zero x, we'll have the maximum electric field. And it's not necessarily B equals A, you know, because if pluses are heavily doped, they will fit, you know, much more into a smaller region. Or if minuses are less, then, you know, they will probably spread much more, or vice versa. So basically, B doesn't have to be equal to A. But there is a formula how this B and A is calculated as well. So to summarize, the fixed ions in this depletion region create the electric fields, and this electric field results in a drift current, and the drift current neutralize the diffusion currents. Okay, so any questions? Okay. We talked in the previous lectures what is a junction drift current. The drift current happens because if there is an electric field, holes have a mobility constant, electrons have a mobility constant, and velocity equals mobility constant times electric fields. So the electric field causes these electrons and holes move with a certain speeds, and then when we increase the electric fields, somehow the velocity saturates at some point, right? There is a physical phenomena which I can explain later, but eventually they come to a saturation. So in equilibrium, somehow the drift current should be equal to the diffusion current, so that this diode has no current flowing on it. So as I mentioned, the diffusion current happens from more to the less. So if you look at the holes, we'll see that because holes are more, the diffusion current is from more to the less. So the holes will flow here. And as I mentioned, there were a lot of ions with plus signs here. So, and we put pluses here, and then there were minuses there at the other side. So, and that caused an electric field, as I mentioned before. And that electric field actually pushes the holes towards the other direction, and that is called drift current, right? So it pushes the holes actually due to this electric field. So holes come due to the diffusion. You can think that way. They are coming, but then they see the electric fields. They are getting forced back. Okay, so then we don't get to see any currents. And the formula for that is I drift hole equals I diffusion hole, and I drift N equals I diffusion N. And you know their formulas. So when I ask you, hey, what is drift current for holes? What is diffusion current for holes? And you should be able to write them. Don't memorize it, but you should know where they are coming from. Okay, so to summarize, the drift current flowing in one direction cancels out the diffusion current flowing in the opposite direction. So the net current becomes 0. Okay. So the next slide. When we have this junction, it's pluses and minuses, the depletion region. As I mentioned, there is an electric field. And when there's an electric field, the voltage is the integral of the electric field. So we can tell that there is a voltage potential over this junction. So when we look at here, we'll see a potential of V, and let's say this reference is minus V, right? So this potential is called built-in potential. And the built-in potential is basically occupied, like this is derived from a bunch of equations. But where it is coming from is actually from equating drift current to the diffusion current. So this is a drift current for holes. And as you know, this is the diffusion constant. This is the mobility constant. And then we multiply both sides with dx. So then we get this equation. And then we take the integration of it from the location x2 to location x1. So which means this one, the holes at x2 and holes at x1. So, and when we write this, this becomes Vx2 minus Vx1 equals this. And this one is basically the voltage potential over that depletion region. And we can call it, for instance, V0, the built-in potential. And the V0 is basically this formula. And we can also write this formula in terms of some other parameters. So it becomes this formula. So that's why because there is an electric field across that depletion junction, That's why we have this built-in potential. And that built-in potential is called basically V0. Okay, and the derivation here is shown here, like how we build it. Okay, what happens if we reverse bias a diode? What does reverse bias mean? So the right side is pluses, left side is minuses, like basically right side is P junction, left side is N junction. And what happens if we provide a voltage source with minus voltage at the right side and plus voltage at the left side? So looking at it, we have plus at the right side. So let's enter plus here from voltage V plus, VR plus. And then we have VR minus at this side, VR minus. Okay, so this plus voltage will attract a lot of currents, a lot of electrons. So all these electrons in this region, like basically in this region, they will flow towards the plus. And similarly, the minus voltage will attract a lot of holes. So all these holes in this region will flow, basically this region, they will start to flow towards the minus. So there won't be any holes left, there won't be any electrons left. So this junction, we lose this part of electrons, we lose this part of holes. So junction becomes much larger. This junction means the region. And this region becomes much larger, and that's how the diode in reverse bias functions. So when this becomes more, and it means it has a higher electric field, right? Because now there are more plus signs, more plus ions, and there's more minus charge ions, and there are more phosphorus at the right side and there are more borons at the left side. So this wider depletion region causes a larger built-in potential, larger built-in electric field. Okay, as I mentioned, wider depletion region, larger built-in electric field across the junction. And how this diode in the reverse bias can be used. So we can use this junction actually as an integrated capacitance. Instead of using a capacitance in microelectronics, we use these PN junctions. And actually, it was in one of my research papers. So when you design some system that is very sensitive to capacitance, you benefit from PN junctions. And the way it works as a capacitance is basically this region, the depletion region, it's a plate capacitance, you can think. There is a plus plate here, and there is a minus plate here. So it's kind of a capacitance with an electric field in the middle. So, and there is this voltage that we supplied here, reverse voltage. So minus to the at the P side and plus at the minus side, N side. And we form the region, right? And if we increase that reverse junction, actually, if we increase the reverse voltage, what happens is this region gets much bigger, because just I explained in the previous slide. And when this region gets much larger, this region becomes less capacitic, because capacitance is inversely proportional to the dimension. Because it gets much larger, the capacitance value of this junction drops. And then we can form an equation that has an input VR2, this becomes your input voltage, and you start the continuous domain change it. And when you continuously change it, you start to continuously change the depletion region and the capacitance. So what happens is characteristics of a integrated circuit capacitance, just like this. So you have a zero potential voltage and you have a fixed depletion region. And then you start to increase your reverse bias. You start to increase the absolute voltage, in the circuits. And when you start to increase, the depletion region starts to increase. And as you can see, the cap goes down. And because the cap goes down, we can formulate it like in a way that the CJ, the initial cap value at voltage of 0 equals to a constant. I'm sorry, the CJ0 is basically the capacitance at voltage 0 is a constant divided by 1 plus VR over built-in potential. So, and then basically this shows you the formula for the capacitance of this PN junction. And when you put all the variables and stuff, all the parameters into the formula, you can reach to this capacitance equation in terms of the dopings. So remember, Na was the doping for acceptors, and D was the doping for phosphorus. And so V0 was the built-in potential that's calculated from the previous slides. And now you are able to calculate your capacitance, right? So, and the capacitance is basically voltage dependent capacitance. Any questions? Okay. How and where do we use it? So this function is very, very important in integrated circuit design because we need to change capacitance in certain designs, in certain circuits. One of them is oscillator. So oscillator works as a function of LC. L is the inductor, C is the capacitance. And the formula for the oscillator is the oscillator frequency equals to 1 over 2 pi divided by square root LC. And when we look at this formula, basically oscillator is used to generate an oscillation frequency. We need these oscillation frequencies to mix other signals most of the time. So we need to change this frequency in the circuit through a different parameter. And this parameter would be VR, for instance. Whenever we change the VR, the C changes, and whenever the C changes, the oscillation frequency changes, right? So obviously you design a circuit now that you can change the frequency because you can change the capacitance. And obviously this is very beneficial because in a chip that is adaptive to the environment, you will want to mix your input frequency with different frequencies. For instance, you got a 2 gigahertz signal, you want to mix it with 1.9 gigahertz. If you got a 2.1 gigahertz signal, probably you want to mix it with 2 gigahertz signal. And that's why this capacitance is very crucial for an oscillator. Okay, this is a very important application of a reverse bias PN junction. And let's go to the next slide. What is a diode in forward bias? So this is the opposite of reverse bias, right? We applied the voltage, VF, and now we applied it as plus sign, applying towards the P, and minus sign, applying towards the N. So probably you can guess that this depletion region now acts the opposite. In the previous one, it was getting bigger, right? And in this one, probably it gets smaller, right? This instead of that. So it was like this, and now it gets smaller instead. And in the reverse diode, reverse bias, it was like this, right? So the depletion width is shortened, and the built-in electric field decreased because the junction is much smaller right now, right? So that this junction, like now, instead of this, it became the smaller one. It became this, for instance. So the built-in electric field now decreases, and that means I have less, less force against the diffusion current. I cannot prevent the pluses flow towards the minority. So there are a lot of pluses here, right? They will want to flow here. There are a lot of minuses here. They will want to flow here. So I have less strength, to say no, don't come, because the electric field in this junction is much less. So they will start the flow, and now the diffusion current becomes the dominant current in the forward bias diodes. And of course, there are formulas how strong it becomes, and that's what we will look in the next slide. So if we compare it with a junction, with a PN diode in equilibrium, as you remember, it was like this. There were majority carriers, there were minority carriers. So comparing it with now with the forward bias, this is the steady state, which means we already applied the voltage. Now we are looking at the carriers inside the bias. You'll see that there is an increase in the minority carriers, right? Instead of here, now we are in a much more higher level compared to a diode in equilibrium. So same for the electrons in the p side. They also increased quite a bit, as you can see. So, and this is basically proving that the holes actually already float towards this side, and the electrons already flow this side, so that actually we have much more electrons and holes as minority carriers compared to before. So as you can see here, the levels are here compared to here, much less. So now we understand that diffusion current becomes the dominant current mechanism in a forward bias junction. And we also understand that the built-in field or the built-in potential gets lower, and the resistance against the diffusion carrier becomes much less. That's why. So that's it for this slide. Do you have any questions? Okay, so this is the formula for the diffusion currents. As you can see, for both electrons, actually for holes in equilibrium and for holes in forward bias. This equation represents this, and this equation represents forward bias. So when we compare these two equations, we understand that there is only one term difference, and that's called V, and that is VF, which is this. And this is basically the bias voltage. So the more you increase your bias voltage towards the built-in potential, the more you let diffusion happen, right? So if you make this VF equal to the V0, if you make it equal to the built-in potential, this will be exponential power 0, which equals 1, right? So what will happen is the holes at the N sides will be equal to holes at the P sides, like as you can see here, because the denominator is 1, right? So what will happen is the holes at one side, holes at the N sides will be equal to the holes at the P side in forward junction. So what does that mean? This curve will become fixed. Like it will start to get like much more like this, right? So any questions? No? Okay. If we look at the diffusion current in forward bias, it's a lot of formulas, and I will send you notes about these formulas. But obviously, we need to understand what these terms and how they affect the holes and electrons. So if we look at, for instance, this first equation, this equation tells us if we increase the voltage, the applied voltage from outside, we increase this exponential term, and this entire term increases, so that the electrons at the P side increase, right? So basically, they start to diffuse much more. And similarly, same thing for the holes. And eventually, this equation comes to a final form, and the equation becomes I total becomes IS, which we call the saturation current that we found it from these equations, times exponential power forward the bias voltage divided by thermal voltage minus 1. And this IS, the saturation current, this one, now is actually that characteristic of that diode. Why it's a characteristic? Because it entirely depends on that semiconductor. How does it entirely depend on that semiconductor? Well, the dN is constant for that semiconductor. dP is constant for that semiconductor. The depletion region, Ln and Np, they are fixed, and the Na, the donors, the acceptors and the donors are constant, and this is Q. It's a fixed number. Ni is constant for a certain semiconductor, such as silicon. You solved it in your quiz. It's a fixed number at a certain temperature, and A is the area. So when you change the physical dimension, basically you can change the current of the saturation current of it, I believe. And then when we calculate the total current, we realize that it's a function of that saturation current, which means the current, the diffusion current in forward bias is a function of saturation current, which means it's a highly dependent function of that semiconductor times it is a highly dependent function of the applied voltage. Okay, and actually the current becomes a very easy formula, right? So this is called the diode current in forward bias. And that's it for this slide. So obviously the summary is diffusion current will increase in order to supply the increase in minority carriers. And this top, all the mathematics are shown. Next slide shows the minority charge gradients. And this gradient shows you that, you know, the flow of the diffusion, the flow of electrons or flow of holes in this depletion region has a certain characteristics. And these minority charges, they shouldn't be constant along the x-axis. You know, basically the it shouldn't be an impulse function. It shouldn't be like this, right? It should rather flow in a homogeneous way. And the gradient happens obviously at some point because of the diffusion. But how it happens is if it is a linear or if it's like a more exponential or polynomial curve like that is determined by the recombination of the minority carriers. So when these electrons and holes, when they try to get into this depletion region, they start to recombine with the others. So those recombination effects basically makes it much more a polynomial curve compared to a linear curve. So the curve becomes much more, as you can see here, much more like this, right? Rather than super linear. And this is due to the recombination of the minority carriers in these regions. Okay, so the next slide shows that the next slide summarizes forward bias condition. So there are a lot of electrons here, and when you look at how they are distributed, you'll see that most electrons actually exist at the far away of the diode, because this is heavily doped with electrons, and this side is heavily doped with holes. But the gradient of it will slowly drop in that region. Okay. Okay. So the next slide shows that these PN junction, these diodes have this current and voltage characteristics. So as I mentioned, every device is supposed to have a current voltage characteristics, because if they don't have it, we cannot use it. We have to know how they operate so that we can use it in our circuits. When you use in the lab, in the ORCAD, like you will be using sometimes non-ideal devices. And those non-ideal devices are actually like designed, they got taped out, they sent to fabrication, they come back, they got measured, and the parameters are found, and those parameters are injected into the simulation. And that's how these simulation tools, are helpful with simulating these circuits. So looking at the PN junction, how this PN junction works, we can summarize it. When it's on equilibrium, which we already mentioned, when there is no voltage applied, we already knew that it draws no current, which means the drift current is actually equals to diffusion current. So that, as I mentioned, the region, the depletion region, has an electric field, and it is not letting the diffusion currents flow. It's forcing it back. So that's why we have no current here. But when we start to forward bias this junction, we start to make this diffusion mechanism much important, and the depletion region gets smaller, right? Because the diffusion, the electric field in that region gets smaller, and when it gets smaller, the diffusion currents start to flow, and now we see the current coming out. And the current is not a linear, but an exponential like this. And because we realize that there are a lot of formulas why, and eventually it saturates at some point. And the reason it saturates is velocity saturation, as we explained in the slides. All the electrons and holes at some point will be subject to kind of saturation because of the recombinations. Like basically, when it starts to move so fast, the electrons start to hit. And when they hit, they cannot gain their speed back. And that is the mechanism that causes saturation. So at some point, it will think it like an explosion, like goes super hot, goes super fast, and then eventually it hits some parts, and then it's explode, and it cannot really come to its original state again. So that's why this velocity saturation happens, because of all the electron particles hitting each other, and they cannot get their speed back. And as we saw in the previous slides, this is the diode equation. And diode says that we have some term called saturation current, and we told that it is a function of semiconductor and it's called IS. And then we told that there is this diode voltage applied outside and it is VD. And then there is this -1 because we need to make sure that this diode doesn't conduct anything. So for instance, let's just apply 0 voltage here into this equation. So when we put 0 volt here, what happens is exponential becomes 1, right? Exponential 0. So exponential 0 is 1, and then 1 minus 1 becomes 0. The current is 0. So yeah, as you can see here in this graph, also as we already learned from the previous slides, yes, when there is no voltage, the diode doesn't conduct any current. And let's apply something like VD minus infinity, right? So exponential minus infinity is 0. 0 minus 1 is 1, minus 1. Minus 1 times saturation current is minus saturation current. And as you see, here we have minus saturation current eventually saturating towards that current when we increase the reverse bias of that junction. Because what happens again when we increase that reverse bias junction, the reverse bias voltage, the depletion region starts to get much larger, and the electric field starts to get much bigger and much bigger, right? So that's why we have the saturation current eventually there. So this is the characteristic of the PN junction. And if we look at the next slide, you'll see that we can combine these PN junctions in parallel. And when we do that, actually, it's just like some kind of a resistor. You can think it's analogies. There are both currents flowing through each of these elements. And you can also model it to PN junctions as this. So let's say there are 2 parallel PN junctions, and that's actually equivalent to this PN junction, same structure, same semiconductor, but 2 times of the area. And you can prove this why, but if you play with the equations, if you look at the saturation current and if you look at the diode equations, you'll realize why this is the case. So looking at the next slides, we are ideally showing how the diode works. So if you remember from the previous slides, we showed that actually it is like this, right? But in ideal model, we model it like 2 straight curves. And this VD on is the voltage when the diodes start to conduct current. And in simple circuits analysis, this is usually around 0.7, 0.8. And this is mostly for silicon. Of course, for every semiconductor, this built-in potential voltage will be changing. And when we cross this built-in potential, the current will start to flow. And for simple reasons, we just digitally show it like, hey, after VD on 0.7, the diode starts to conduct a current. So this current doesn't mean it is infinite. It's a current that is dependent on the circuits. So in non-ideal case, actually every diode, it will have a resistance. So connected with this diode, you will see that a resistance exists, right? So this is in the non-ideal situation. And you know, when we ask you, just like in your homework, there was a battery, and in the non-ideal situation, there was a resistance in series connected to it. So similar with this one. And looking at this characteristics, ideal characteristics, we can say that the diode starts to work like the basically operates with forward bias and flow current when VD bigger than VD on, diode on voltage. When the VD is less than VD on, basically applied voltage is less than the diode on voltage, the diode is off, which shows that we can use this diode as a switch. So you apply less than VD on, you open the circuit. You apply more than VD on, then you basically connect the circuit. When you connect the circuit, this diode will have a plus and minus potential on it. As you can see, it's represented like that. So there will be a plus and there will be a minus on it. And this is usually, as I mentioned, 0.7 to 0.8. So you usually, most of the time, use these diodes as also switches. You know, as you remember in the reverse junction mode, we also use it as a capacitance. So as you can see, diodes are really valuable to mimic certain elements, and we will benefit from them in certain applications. So if we look at a simple circuit to make some calculations, this is a circuit we applied Vx, there's a resistance, there's a diode. And just doing a simple Kirchhoff voltage law, the Vx equals Ix, let's say current is Ix flowing here. And so the Ohm's law, the voltage drop across this R1 is Ix times R1. And the voltage drop over this diode, as we mentioned, is usually 0.7 to 0.8, but we don't know exactly how much. So we call it VD. And this diode current, as you remember, is a function of saturation currents and so on. And this is from the previous slides. And then now we have this function. The two unknowns are Vx and Ix. And if we know the Vx, if we know how much voltage source we are applying, then it won't be any unknown. So the only unknowns will be Ix, and Ix is easily found from this equation since we know the rest. We know the saturation currents from the characteristic of the diodes. We know R1. We know the applied voltage source, so we can find Ix. And this is for instance, it depends on the voltage, obviously. When Vx is applied as 3 volts, we have an Ix of 2.2. When it is 1 volt, let's say, it's 0.2 milliamps. If we apply, for instance, 0.5 volts, what happens? Do you have any thoughts about that? Let's say this is 4 volts.
No current?
Yes. Why there is no current?
Because the drift is not enough to pass.
Yep, that's a good explanation. Because when it is 0.4 volts, the depletion region is still big. It's not small. So the easy way to explain this, the turn-on voltage of this diode, as I mentioned to you, it's 0.8 to 0.7 to 0.8 volts. So if this is 0.7 to 0.8 volts, and if this is 0.4 volt here, I'm bringing it here, right? Because it's the same node. Well, how will be current flowing towards the diode, right? The current always from plus to the minus on the diode. Otherwise, it is reverse current and it's very, very, very small. So to operate this diode, we should know that the plus sign is much bigger than the minus sign. What is much bigger? much bigger than 0.7, 0.8. If this is 0.9, for instance, then now, or if this is 0.8, now we'll start to have current flowing, because this 0.8 volt will be enough to force this diode junction get smaller and have the diffusion current flow. And now this R1 will be happy because it will have some current on it, so it will warm up other people. So there will be some power dissipated on it, right? So that's how we use these diodes as switches. Okay, so the next one is Zener diodes. And the Zener, the reverse breakdown. So we already know that at the right side, the diode operates like this. It has the IV characteristics. And we were saying that at the right side, there is this part where the saturation current starts to flow, a very, very small current at the reverse bias. But then at some point, a breakdown occurs, and this happens at a very high minus voltage. And that is a phenomena in diodes. And now we won't really get into so many details why, but just know that this phenomena exists in diodes, that when you apply a very, very high reverse voltage, okay, the depletion region gets bigger, it gets bigger, and it eventually breaks down because the diode has a certain length, right? How much the depletion region can get bigger. So eventually the atomic characteristics, the quantum characteristics of the device will start to be get bothered by this phenomena, and then the device doesn't operate normal anymore. And then you will see a huge current flowing in the opposite direction. Then that's called the reverse breakdown. So the other breakdown mechanism is called Zener or avalanche breakdown. And the Zener breakdown is basically a result of the large electric field inside the depletion region. It's very similar to the previous breakdown because, as I mentioned, the depletion region gets bigger, and eventually there's a huge electric field, and that electric field causes the electrons and holes, basically break from their bonds, right? It doesn't like function the way that it's supposed to function. And this is called the Zener breakdown. But the avalanche breakdown has a different characteristics. It's the result of electrons and holes colliding with the fixed ions. So in the first one, in the previous slides, or at the left side pictures, the Zener breakdown has a different characteristics breakdown than the avalanche breakdown. So in the Zener breakdown, the depletion region gets much bigger, the electric field gets so much bigger, and it forces electrons and holes break their covalent bonds. In the avalanche breakdown, the electrons and holes in the depletion region starts to collide with the fixed ions inside the depletion region. Normally they were supposed to stay outside, right? The electrons are supposed to stay here, the holes are supposed to stay here, and there were supposed to be a lot of ions here, and there were supposed to be a lot of ions at the right side, right? So but now they start to get inside this region, and when they start to collide with the ions, like a different phenomenon called avalanche breakdown happens, and the circuits now operates in a much different way than the Zener breakdown, but it's still a breakdown. So the breakdown basically means a lot of unpredictable currents in the other direction. So the characteristics is still like this, like the characteristics is still similar. It's the breakdown, but the way that it happens is a totally different phenomena. Okay, do you have any questions?
Sir, does this cause anything like heat dissipation or something like that?
I mean, I'm sure there will be a dissipation of heat, because why heat occurs is basically you push the limits, right? Actually, when you heat the kettle in the resistor, you are providing so much current into that resistor, and you make the particles hit each other, and they somehow collide and provide some kind of a reaction, right? So it's similar here. You know, you provide so much electric current and you force them break their bonds, right? And this energy is supposed to go at somewhere, like at some point. I'm sure there's a lot of heat. So if you touch a diode in the breakdown, I am sure it will heat your fingers. It will warm your finger. Similar to a resistor. If you were in the lab, or if in the 202, maybe you realize that if you put so much current on a resistor, and when you touch the resistor, your hands eventually can sense that resistance heat. So that's how it is, not just in PN junction, same in transistor. When you burn a transistor, it's the same way, and because you push the limits of the device.